Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.7. Optimization problems.
Lesson 3. Constructing the cheapest box.
So let's go ahead and look at this example. You're asked to construct a closed rectangular box with a square base. So it's going to be a rectangular box. The base is actually a square and it's closed, meaning that you don't have like an opening on the top. The volume of this box is supposed to be 12 cubic feet. And does that make sense for a unit of volume, cubic feet? It does, because remember, to get a volume of a box, you do the length times the width times the height. So if they're all in terms of feet, it would be feet times feet times feet, which is cubic feet. Okay. The top is to be made of a metal that costs $2 per square foot. So this top is made from something that costs $2 per square foot. And the remaining sides are to be made of some kind of plastic that costs only $1 per square foot. So that means these remaining four sides, this one, the one that's in the back, and the one that's, if I can draw it here, that's all the way around here, those four sides, and also the bottom is one of the other sides that's left over. All of those cost $1 per square foot. So the four sides and also this one on the bottom is $1 per square foot. Okay. And it says find the dimensions that minimize the cost. Okay, well, this sounds really hard, but let's go ahead and apply our 5 steps. And I think you'll see that if you go through it step by step, it's really not so bad. First step, remember, we're supposed to draw a picture and label all of the things that could vary in the problem with variables. And label anything that's a constant with a constant. I don't think we have any dimensions here that stay constant. So the box could look like a lot of different things. It could be tall and skinny or fat and squat. So the dimensions of the box could vary. So maybe I'll call the height of my box y. So y is going to be the height. And I'll call the width down here of my box x. So that's this dimension, y is this dimension. What about this dimension, the depth of my box? Remember what it said about the base? It said it was a square base. So if this side is x, that would mean this side would also have to be x. Does that make sense? Because it's square, and so whatever this dimension is, it has to match this dimension. Those could vary, but they have to match each other. So my box is an x by y high box, y high. So now we've drawn the picture. Well, the picture was drawn for us, but we've labeled everything that can vary in the problem with variables. Now, second step, and here's where I want you to pause the video. Try to find the function, and remember, this is the function that we mark with a star because it's the main function we're concentrating on, and it's the function that you're asked to either maximize or minimize. So try to decide for yourself, what am I asked to maximize or minimize? And write that down in words, and if you can, try to start to think about how you would write down that function in terms of the dimensions we've put down, the x and the y. So take a moment and do that, and if you get stumped figuring out how to write down the function in terms of x and y, just start the video again and we'll go through it together. Okay, let's try going through this together. Remember, what we are asked to minimize in this case is the cost. So it says find the dimensions, in other words, find the x and the y and the other x here, that would end up giving you a box of the smallest possible cost. We want to minimize, in this case, the cost. I think all the other examples we looked at, you were trying to maximize something, but here we want to minimize the cost. So we want to minimize and I'll just write that in since that's a little unusual, the cost of the box. And remember that the cost of the box is found by finding the cost of a bunch of things. It would be the cost of the top, so I'll write cost of the box is equal to cost of the top plus, I'll put cost of 4 sides, plus the cost of the bottom. We'll sort of break it up that way. And let's see if we can figure out what each of those costs are. Let's concentrate first on the top. So if I want to know how much does this top cost, well, remember what we said in our little preliminary discussion. I'm going to put that back up here for a second. We said that the cost, in this case just of the top, would be the price per square foot times the number of square feet, which is another way of saying the area. So we're going to do the price per square foot times how many square feet there are, in other words, times the area of that top. So if I want the cost of the top, I would do its price per square foot. Well, we're told it's $2 per square foot, so that's the cost. It's $2, and if you want to, you can put in the units per square feet, or you can write per foot squared, same thing. And I want to multiply that cost per square foot times the number of square feet. In other words, times the area of the top. But what is the area of the top? Well, remember the top is a square. It has to match the bottom since this is a rectangular box and we are told that the bottom is a square base. So the top is also a square. It's an x by x square, so its area would be x times x, or x squared. So there are x squared square feet in the top. So if you want to, you can put the units on there and say it's x squared square feet. X feet times x feet gives you x squared square feet. That is the cost of the top. If we want to simplify a little with the units, you notice the square feet will actually drop out, and the cost of just the top would be $2 times x squared, or 2x squared, and that would now be in units of dollars. You could put a dollar sign there if you want to. I'm going to leave that off just to make it a little bit cleaner. Well, that's the cost of the top. Now let's move to the cost of the 4 sides and the cost of the bottom. And if you had trouble figuring out this cost function, I'd like you to pause the video again, see if you can figure out what the cost of the 4 sides would be, remembering that they're $1 per square foot, and what the cost of the bottom is, remembering that that is also $1 per square foot. The top, remember, was made of metal, which cost more, but all the other sides, the other 5 sides, were made of something that was plastic, and it was cheaper. It cost only $1 per square foot. So pause the video for a moment and see if you can figure out this thing, the cost of the 4 sides, and this thing, the cost of the bottom. Well, for the 4 sides, we said their price is $1 per square foot. And then we have to multiply by how many square feet are in those 4 sides. Well, if you look at any of the sides, because the base happens to be a square, all of the sides have the same area. Notice the area of this front side would be x times y, or xy. So the area of one of these 4 sides would be xy. And see, you can see here that this side would also be x by y, so that's another xy. The back is another xy, and this far left side is an xy. So xy plus xy plus xy plus xy, that's 4xy. That's the total area of the 4 sides. So we take the price per square foot and we multiply by the area, the number of square feet, and so it would be 4xy feet squared. And again, you notice the square feet cancel out. And so the cost of those 4 sides would be 1 times 4xy. That would be in units of dollars. So this is just 1 times 4 would be 4xy. And you could put a dollar sign on there, but I'm going to leave that off again. The cost of the bottom, well, that's going to be the price per square foot, which is $1 per square foot, times the number of square feet. I'm going to erase this y here because it's going to confuse us. The number of square feet in the bottom, well, it's a square that's x by x, so the number of square feet would be x squared square feet. The square feet cancel out again. It's a little hard to read, sorry about that. So I have a plus $1 times x squared would be x squared dollars. And so I end up with this as my cost function. It's 2x squared plus 4xy plus x squared. Let's just simplify it because I can see that I could add like terms together. I would have a total of 3x squared plus 4xy. That is the function that I want to find the minimum of. So that's the main function that I'm going to be concentrating on. But just as in our earlier examples, this unfortunately is a function of two variables. We want it to be written as a function of just one variable. And the question is, can we do that? Can we rewrite this as a function of just x or just y? We can if we go ahead and try to find a constraint equation. And I want you to take a moment, stop the video, and see if you can decide what it is that constrains this problem. I could make it a really cheap box by making it super tiny. Maybe make x equal to 0 and y equal to 0 and have something with no volume at all, and that wouldn't cost anything at all. That would minimize my cost. But there's a reason that I'm not allowed to make this box as tiny as I want to. So I want you to go through the problem and see what's constraining the x and the y so they can't just be as small as we want. And if you can figure out what's constraining the problem physically, then go ahead and see if you can write that constraint down as an equation that involves x, y, and numbers. Okay, well, let's go ahead and try to figure out the constraint. So that's what we're concentrating on next here. And let's see, it says you're asked to construct a closed rectangular box with a square base and a volume of 12 cubic feet. You notice this box can't be really tiny with x equals 0 and y equals 0, no volume at all, because we want to have a box that has exactly 12 cubic feet of volume inside it. So unfortunately, we can't just make x and y both 0 and make the cost 0, because we have to build a container that can house 12 cubic feet of whatever we want to put in there. So it has to have a volume of 12 cubic feet. Well, what is the volume of a box? The volume of a box, a rectangular box, a right rectangular box, is just the length times the width times the height of that box. So the volume in this case is prescribed for us. The volume has to be 12 cubic feet. So the volume must be 12. The length of this box is x. The width of this box is x. And the height, I sort of scratched it out here because there wasn't room for it. Let me put it over here. The height of this box is what we were calling y. So our constraint equation, the equation that involves x, y together with a number, is just 12 equals x squared y. Well, that's nice. There's our constraint equation. Now the question becomes, what are we going to do with that constraint equation? And so what I would like you to do is to think about step 4. Pause the video and see if you can do step 4, which is to rewrite our main function. That means our cost function, which remember was this. Cost is equal to 3x squared plus 4xy. We want to rewrite that in terms of one variable instead of two variables. So see if you can figure out how to do that, and then start the video again. Well, let's go ahead and do this together. Remember that you can always take your constraint equation, which from the last page was this, 12 is equal to x squared times y, and solve for one variable in terms of the other. You can pick x to isolate or y to isolate, but it looks like it's easier to isolate y. If you tried to isolate x, it would involve a square root. So let's go ahead and write down y would be equal to 12 over x squared, just dividing both sides by x squared. And now I've rewritten y in terms of x. And what do I do with that? Well, I wanted to write this as a function of just one variable. And I can do that if I then substitute this expression in for y in the function that I want to minimize. So let me go ahead and plug in. I would get the cost is 3x squared plus 4x times 12 over x squared. So that is my cost, and I'm just going to simplify it a little bit. Let's see, one of these x's would cancel with the x that's up here, so it looks like I would get a cost that is equal to 3x squared plus 48 over x. I'm actually going to write it this way as 48x to the negative 1. It's 48 over x. That's my cost function, and if I want to now I can write it as c of x, and that's because it's a function purely of x now, purely a function of one variable. Let's go ahead and think a little bit about the largest and the smallest values x can take on would be for this particular problem. And I just want to do it together because for this particular problem it's a little bit trickier than the ones that we looked at earlier. First of all, I know that because x is the dimension of a box, that x can't be something that is negative. So I know that x has to be greater than or equal to 0. In the previous examples that we looked at, x could be equal to 0 mathematically in our constraint equation. But let's think about whether that would be possible in this constraint equation. If I made x equal to 0, could I find a y so that y times 0 squared would give me the prescribed volume of 12? Unfortunately, I could not. No matter how big I make y, any finite, even huge number times 0 squared is going to give me 0, and there's no way I'm going to get this value of 12. So unfortunately in this case, x cannot be equal to 0. It could be something that's very small, but it has to be at least slightly greater than 0. So x could be something very tiny. For example, just to let you see that, let me get my sponge again. I'm trying to get my finger wet with my sponge. So x could be something very tiny. For example, x could be 0.1. And when I plug it into the constraint equation, I would get 0.1 squared, which is 0.01. So I get 12 equals 0.01 times y. And you notice that you can solve for y. You can divide both sides by this. Y just comes out to be really large. You'd end up, if you invert this, it's equal to 100, so you'd end up with y equals 1200. So y can be something very small and positive, and you can still find a x can be something very small and positive. You can still find a y value that works, but it'll be something rather large. The same kind of logic works for y. If you think about y in this constraint equation, it also cannot be equal to 0. Y could be something very small, but it can't be equal to 0 because 0 times anything we choose for x, quantity squared, will still give me 0 and won't be equal to 12. So y can be very small as long as I make my x big enough to compensate. For example, if I had something such as y equals, I don't know, 0.1 again. Well, I could go ahead and divide both sides by 0.1. I'd get 120 equals x squared, and x would just have to be a fairly large number. It would have to be the square root of 120. And the smaller I make my y, the bigger x would have to be in response to get this product to end up equaling the finite value of 12. So if I make y very, very tiny, it means my x is going to have to be larger and larger to compensate and make this product equal to the number 12. What that means is that the range of values for x would be from 0, strictly greater than 0, and could really go up to any size number. X could be very, very large. We would just have to choose an even tinier y, and then this product would still be equal to 12. So it's a little tricky in this case to get the range of values, but we are really looking for the minimum cost of this function c of x for x's on this interval from 0 to infinity. Okay, let's go ahead and think about step 5. We are asked to find the absolute minimum cost. So I'll say the absolute minimum c value. And we are asked to find it on this particular interval. Well, if you look at this particular function, c of x, I'm going to write it for a moment without that negative exponent. It's 48 over x. It is a function that is continuous on this interval. So this is a continuous function on this open interval from 0 to infinity, because we're excluding the one place where this function would fail to be continuous, which is where this denominator is 0, and that isn't included in this interval because it's an open interval and we're not including 0. So it is continuous on this interval, but unfortunately this interval is an open interval. It's not a closed interval. And so we can't apply our quick two-step method to find the absolute minimum value of c. Remember, with the two-step method, that works if I have a continuous function, but it has to be on a closed interval, not an open interval. It has to have endpoint values that we can plug back into c, and we don't have any endpoint values in this case. That doesn't mean that we can't do the problem, it just means that we can't use that two-step method to do the problem. So let's see how we would find the absolute minimum. We start by finding the local mins. So we look for local mins, and we just sort of analyze enough of the function that we know enough about the graph that we can definitively say, yes, we've found the absolute minimum. So we usually start by trying to find the local minimums of this function. And how do I do that? I find the critical numbers. So I'll go ahead and find the critical numbers of c, and c of x again is equal to 3 x squared plus, and I'm going to go back to using the negative exponent, 48x to the negative 1. So to find the critical numbers, I find the derivative and I look for where it's 0 or where it's undefined. So c prime would be 6x minus 48x to the negative 2. All right, that looks fine. Let me go ahead and write this without a negative exponent. It's 6x minus 48 over x squared. And as usual, it's not very nice to have two separate terms if you're trying to decide where that expression is positive and where it's negative. Much easier to have a single fraction. So let me write the 6x as 6x over 1. What do I have to multiply the top and bottom by to get a common denominator? Looks like I need an x squared there. So I'll put an x squared in the top and the bottom. And it looks like I end up with this 6x cubed minus 48 all divided by x squared. And let me just go ahead and write that in factored form. I could pull out a 6. I would have 6 times x squared minus, I need an 8. That's an x cubed, excuse me, all divided by x squared. And remember, we're looking for any values that make this expression 0 or make it undefined. It'll be 0 when the top is 0. X cubed minus 8 will be 0 when x is 2, because 2 cubed would be 8, minus 8 would give me 0. So one of my critical numbers is x equals 2. That makes my derivative 0. My derivative c prime will be undefined when the denominator is 0, and that would be true when x equals 0. That actually falls outside of my interval. Remember, it's an open interval from 0 to infinity, so it's actually not in my interval. I don't have to consider this critical number. I only want the absolute minimum of this function on this open interval. It does not include 0. Well, let's go ahead and see if we can analyze this critical number and decide whether it is at least a local minimum, even if we don't yet know whether it is an absolute minimum of the cost function. So how do I analyze a critical number if I'm not working with a closed interval as we were in the earlier examples? The only thing I can really do is to draw a number line and go back to our first derivative test and check the sign of my function's derivative, in other words, the sign of c prime of x, to the right and the left of the only critical number that's in its interval. And remember that the open interval we're talking about is from 0 off to positive infinity. So we're not considering 0 or anything to the left of 0 for the physical problem that we're doing. Let's check the sign of c prime. We can check the sign of c prime to the right and left of 2 just by choosing test numbers. Maybe a good test number to the right of 2 might be 3. And if I plug it into this expression, 3 cubed would be 27 minus 8, that's definitely positive, times 6, that's positive. The bottom is always positive for x's in this open interval, and so the overall sign of this fractional expression will be positive to the right of 2. To the left of 2, I need to choose something in my interval, so maybe I'll choose the number 1 as a test value to the left of 2. And when I plug 1 into this expression, I'd get 1 cubed minus 8, that's negative 7, that's negative, times 6 is positive, divided by something that's always positive, and it looks like my sign does flip to become negative on the other side of my critical number 2. Well, what does that mean about our function c of x? It means that the function c is decreasing to the left of 2 and increasing to the right of 2. Oh, well, okay, that's good, because that means right at 2, what has to happen? I must have a low point here. So I must have a local minimum at 2. So this point right at x equal 2 must be a local minimum. Now, all we really proved technically is that this is a local minimum. We've only shown that it's a local minimum, and we really would like to find the absolute minimum cost. We want to know that's the lowest cost anywhere on our graph of c of x. So I want you to think for a moment about what the graph of c of x has to look like. I don't want to actually graph c of x completely if I don't have to. That would be one way to find the absolute min. But what we've found is that there is a local minimum at the value x equal 2. So whatever that minimum cost is, it's some value here. Remember, we are only looking at x values that are from 0 to positive infinity. So we are only looking at that open interval. And we also said that this is a continuous function on that open interval. So what do we have? We have a local minimum here. We have no other local maximum or other local minimums. It means that the function is going down until I hit that local min, and it is going up forever after that. So the function is going down till I hit this, and then it increases from then on. It can't turn around and go below this local minimum. Why couldn't it do that? Well, we found only one extreme point, this one. If it were to turn around and it's a continuous function, it means we would have found another point up here that would have to be a local max. And we did not. There were no other critical numbers in our interval from 0 to infinity. So this cannot happen. The function has to continue going up forever. And from that information, without really going through and graphing c of x carefully, or even finding the y value, or I should say the c value that corresponds to this x value of 2, so not only is x equal to a local minimum, it has to be the absolute minimum, or correspond to the absolute minimum cost. And that will always be true if you have a function that's continuous on your interval and there's only one extreme value, either a local min or a local max. If it's a local min, it will also be an absolute minimum value, and if it's a local max, it will also have to be an absolute maximum value. Okay, so we know that x equals 2 corresponds to the absolute minimum cost, and the units on that would be units of feet. X is one of the dimensions of our box. And so far what we found out is that our box has a base that is 2 feet by 2 feet. Remember that x was the dimensions of that square base, x by x. Well, the only thing we have to do now is to find the dimensions that minimize the cost. We found the x dimension, but we have to also figure out what the y dimension on this box is. So that's our last step, is to figure out what the corresponding y value is. And how do I find the corresponding y value for our box? Usually it's easiest to go back to the constraint equation to find that, and I like to go back to the point where I had solved for y in terms of x. So let's go back up here to step 4. You notice I had solved for y in terms of x right here. Y was 12 over x squared. And I could go back to my original constraint equation, or I could even use the fact that I know the volume of this box is equal to 12. But I've already done all the work of solving for y in terms of x up here, so I might as well take advantage of that. Y is equal to 12 over x squared, and we've just gotten through saying that x equal 2 corresponds to the minimum cost, and so I just solved for y. 12 over 2 squared would be 12 over 4, that's 3, and that would be in units of feet again. So remember that y was the height of our box. I guess I could put it right here. And so it's kind of a squatty box. It's not quite a cube, but it's 2 feet by 2 feet by 3 feet. My picture's perhaps off a little bit. So the x dimension is 2 feet, the y dimension is 3 feet, and usually in this kind of problem where you're giving dimensions of a box, we will write our final answer as, let me move this up a little bit so that I have some room to write here. We usually write that the dimensions of the box are, and we just say 2 feet by, or you can put a big X there, 2 feet by 3 feet high. So you're really saying it's 2 feet wide by 2 feet deep by 3 feet high. And that's how we would present our final answer. Okay, well, just a couple of remarks about optimization problems in general. As you've seen in these examples, each one is rather different and presents its own challenges, whether it's coming up with the function that we are asked to maximize or minimize, or finding the constraint equation, or finding the range of x values on which we're considering our function, or whether it's just the mechanics of actually finding the derivative and simplifying that expression. That itself can be a challenge. So you want to be patient with yourself and realize that you're going to attempt these problems in your homework, and you may get stuck at places. You want to ask your teacher or ask in your math lab or your tutor to help you whenever you get stuck, but you will find that as you practice and do more and more of these problems, you'll be able to get farther and farther without any help, deeper and deeper into each problem. And don't forget that just struggling with these and thinking about them is totally normal. Nobody can just do these problems without any difficulty. They require hard thinking, and of course hard thinking means that your brain is creating new neurons and new connections. And so doing these optimization problems, like most mathematics, literally makes you smarter. Your brain structure actually changes doing mathematics. And I've watched students over the semester get just smarter and smarter, quicker and quicker, more and more able to take a lot of different disparate information and put it all together into a solution to a very difficult problem. So practice does make perfect in this case, and just be patient with yourself, and don't worry if it's a struggle at times. That means you're on the right track.